Hi, my name is Mirabel Havet, and today I'm presenting Lab 4 Circuits for Physics 2212. So, the purpose of this lab is listed below, but essentially it's to understand how a circuit functions. Okay, so in this experiment, we had two experiments, really. The first one was, as you can see on the right here, it was kind of set up as just a simple circuit, and it was meant to describe how current changes while passing through a wire. And the models and physics principles used were that an ammeter measures current in amps, and a voltmeter measures voltage in volts. And there are some more physics principles that we observed throughout this experiment and that we also used to have more quantitative results, but we'll go over that later. The main results of this experiment is that the current decreases as it passes through resistors. The system is the circuit, and the surroundings are everything outside the circuit. And then again, set up the way it is in the left or the right. The initial conditions are a 3-volt battery, which is two 1.5-volt batteries, a 47 ohm resistor, and a 100 ohm resistor. So the second experiment in this experiment was one in which we added a capacitor to a circuit to see how it affected the flow of current. And the main physics principles used were that a capacitor uh, measures capacitance, or doesn't measure necessarily capacitance, but carries a certain capacitance in farads, and that the light bulb can act as a resistor. Also, a capacitor, essentially what it is two parallel plates that become charged in the equal but opposite magnitude of charge, if that makes sense. Because technically electrons are not allowed to pass in between these two plates, and so capacitors just grow in charge over time until they reach their total charge, their like max charge, and then that's when a current will stop. And so we observed this. We observed that when you charge a capacitor, the light bulbs will dim because again, this current is slowing down, or like the current is coming to a stop as the capacitor comes to a full charge. And then when you drain the capacitor, you also see that it dims. And this is that lower picture where the battery is not involved, but essentially the current travels just in the opposite direction to balance that out. And we noticed that when we charge the capacitor, it was slower than when you drain the capacitor, this change in light. Also, that when you have two bulbs, that the current is slower um, because there's more resistance. So the system, again, is a circuit, and the surroundings are everything outside the circuit. The initial conditions are 10 ohm bulbs. We have two here, so it's 20 ohms of resistance overall, a 9-volt battery, and a zero point 0.2 farads capacitor. So the other physics principles used are the conservation of energy, which essentially is going to say that the potential differences added together are all going to equal 0. And these two formulas right here, which explain the relationship between current, potential difference, resistance, charge, and capacitance. Okay, so these are our assessments from the first experiment. Our possible errors and assumptions are that no current is being lost, and the voltmeter and the ammeter are accurately measuring the data. The ammeter, when inserted backwards, reads the same magnitude but opposite sign because it reads the current essentially going in the opposite direction. And then the sum of the individual potential differences for a round trip should be 0 because all energy is conserved. This graph in the corner here is showing the current and the change of current as you go through this circuit, and you see that on the bottom. And the steeper the line, the greater the electric field at that point. So the assessment for the second experiment, similar assumptions and possible errors that no current is being lost, and the energy stays within the system, and that the electric fields in the connecting wires are negligible, and this is to ensure that the conservation of energy is maintained. And so if you look at this sequence of equations written out here, that led us to find this RC, which rounded up to 4, and that is ideally what the RC would be following these equations. And this is the RC for the second circuit, in which you had that 20 ohm resistor and then that capacitor as well. And this is a graph of what that would look like, just drawn out roughly. Okay, so these two next questions, think about it, are asking us to compare real life to the simulation that was given. Um, And a real ammeter has some resistance, which will reduce the current, leading to less precise readings compared to that in a computer. So that's one difference. And then also in real life, it'll probably take longer for the capacitor to reach full charge because the model represents ideal electron flow with no collisions and a parallel trajectory for each electron, which doesn't always happen in real life. Thank you.